Welcome to the Explainer. Today, we're setting up for an absolutely incredible journey. We're going to look at the evolution of computing hardware, specifically how our machines managed to shrink so dramatically in physical size, while at the exact same time experiencing this explosive exponential boom in processing power. It's a story of just mind-blowing engineering, and as you'll see, mapping out this visual timeline shows just how drastic this shift really was.
Okay, let's dive right into this. Here's our chronological roadmap for today. We're covering the first digital giants, the stored program revolution, the silicon switch revolution, the microprocessor speedrun, 5 generations of computing, and finally, the modern computing ecosystem.
Starting with Section 1, the first digital giants.
So, to really understand how far we've come, we have to start at the absolute dawn of electronic digital computing. The shift away from purely mechanical systems was driven by digital switching architectures utilizing binary, ones and zeros. Between 1937 and 1942, the Atanasoff-Berry computer, or ABC, pioneered this whole concept. It was the world's very first true digital electronic computer. But to really grasp the sheer scale of this era, we gotta look at the military behemoth born in 1946, the ENIAC. 18,000. That is the staggering number of vacuum tubes required just to run it. The physical scale of this machine was, quite frankly, absurd. It consumed 180,000 watts of electrical power and occupied 1,800 square feet of floor space. And here was the biggest bottleneck. If you wanted to run a different program, you couldn't just click an app. No way. You had to initiate a completely tedious manual rewiring of the hardware switches. And this comparison brilliantly illustrates the exact trajectory of computing history. On one side, we have the monstrous 1,800 square foot ENIAC from 1946. On the other side, the Intel 4004 chip released in 1971, which was a tiny 4-bit microcomputer set. Despite fitting right on your fingertip, the 4004 ran at 108 kilohertz and processed 60,000 operations per second. It matched the exact raw computing power of the massive ENIAC. Crazy, right? In just 25 years, we went from a room-sized heater to a chip you could literally drop and lose in the carpet. Moving right along to Section 2, the stored program revolution. Now, you might be wondering, how on earth do we move past the era of plugging and unplugging cables just to change a program? Well, we needed a conceptual blueprint that would solve that manual hardware rewiring bottleneck and basically change computing forever. The answer was the von Neumann architecture, also known as the stored program technique. This foundational concept meant storing programs directly inside the machine's memory. By utilizing random access memory, or RAM, a computer could hold programs and data temporarily during execution. Suddenly, machines like the EDIVAC and the UNIVAC I didn't need to be physically rebuilt from scratch for new tasks. In fact, the UNIVAC I utilized this exact architecture to become the first true general-purpose commercial computer. It effectively moved computing out of the military base and straight into the business world.
Which brings us to Section 3, the silicon switch revolution.
Okay, so with the software side conceptually solved by stored programs, the physical hardware urgently needed to catch up. To physically shrink these machines, engineers went on what I like to call the ultimate quest to shrink the switch, the core component that controls the flow of electricity. Step 1 was vacuum tubes. As we saw, they were massive, pulled heavy current, generated debilitating heat, and had incredibly high failure rates. Step 2, though, it revolutionized everything: transistors. They were these small, lightning-fast, highly energy-efficient electronic switches that fundamentally shrank system requirements. And finally, Step 3, integrated circuits, or ICs. Engineers figured out how to pack multi-millions of transistors onto single silicon dies. This was the exact leap that made battery-powered, handheld computing physically possible.
Now, what's really interesting about this slide is that vacuum tubes aren't entirely dead. Interestingly enough, while they are completely obsolete for modern computing due to all that heat and size, they actually survive today in high-end audio engineering. Audiophiles still prize them because, surprisingly, vacuum tubes produce a warmer, much richer sound profile than modern transistors do. Next up, Section 4, the microprocessor speedrun. All right, buckle up, because with integrated circuits finally in play, processor speeds, which are measured in hertz or clock cycles per second, just began to explode exponentially. In 1970, the Intel 1103 hits the market as the very first mainstream DRAM chip. The very next year, the Intel 4004 debuted with 2,300 transistors. Fast forward a decade to 1981, and the Intel 8086 and 8088 families are actually powering the historic, original IBM personal computer.
Just 4 years later, in 1985, the Intel 386 drops, a 32-bit architecture milestone that absolutely shattered the 5 million instructions per second, or MIPS, barrier. And the speed run continues. 1989 brings the Intel 486, integrating a math coprocessor that incredibly matched actual mainframe baselines. In 1993, Intel abandons numbering their chips altogether and introduces the trademark-protected Pentium name just to fend off competitors. 1997 introduces the Pentium 2, which temporarily moved from flat chips into a really unique cartridge architecture. And then we hit the massive 2003 battle. AMD launches the 64-bit Athlon 64 with over 105 million transistors, while Intel counters with the Pentium 4 Extreme Edition, packing a staggering 178 million transistors onto a single unit. Let's look at Section 5, 5 generations of computing. Let's actually take a quick breath and slow the pace down slightly here. We just witnessed decades of frantic, chaotic technological evolution. To really grasp this history, computer scientists formally categorize the last 80 years into distinct eras. So the crucial point to take away from this matrix is that when we categorize this history, the defining factor is always the core switching component. The first gen relied on vacuum tubes, massive heat, and basic machine language. The second gen brought in transistors and early high-level languages. The third gen introduced those integrated circuits and commercial software. The fourth gen, which we are honestly still largely scaling up today, brought microprocessors, massive storage, and early robotics. Finally, the conceptual fifth generation shifts the entire focus toward the native implementation of artificial intelligence and advanced symbolic reasoning. And finally, Section 6, the modern computing ecosystem. So that massive journey of hardware miniaturization and power scaling ultimately enabled the incredibly diverse macro categories of computers that we rely on today. At the very top tier, we have the absolute titans of computing. Supercomputers are the single most powerful systems globally, coordinating thousands of microprocessors to simulate things like galactic tracking or complex global weather patterns. Right beside them are mainframes. These are massive, highly centralized systems built to dedicate immense processing pipelines securely for thousands of active concurrent users. They're the ones running things like global banking engines and airline reservation networks.
Let's move to see how this builds out to the user level with terminals. To interact with those massive mainframes, users have to connect remotely. A dumb terminal has absolutely zero local processing power. It is purely a remote screen and keyboard relying entirely on the mainframe. An intelligent terminal, on the other hand, offers limited local processing capabilities, though it generally still lacks independent local data storage. Now, bridging the structural gap beneath those mainframes, we have the mid-tier networking backbone. Mini-computers fill the corporate market gap, serving hundreds of users at once rather than thousands. Alongside them are network servers. These are dedicated machines designed to manage interconnected client resources securely, whether that's routing your internet via proxy server, storing complex records on a database server, or just managing your company's email server. Shrinking the hardware even further created the single-user microcomputer space, which you definitely know better as personal computers, or PCs. This broad category is split largely by form factor. You have your stationary desktops and high-performance workstations used by engineers and 3D animators. Then, as batteries and components became much lighter, we got foldable notebooks and laptops, and eventually highly specialized tablet PCs designed for direct screen interaction using a digital stylus. Finally, we reach the ultimate miniaturized powerhouses. The shrinking of the integrated circuit gave rise to pocket-sized personal digital assistants, or PDAs, which were traditionally used for calendars and contacts. But this directly evolved into the modern smartphone, an architecture that successfully combines cellular communication, media engines, high-resolution digital cameras, and full internet accessibility right there in your pocket. Which brings us to the end of our timeline, and it really leaves us with a staggering realization. In roughly 60 years, human engineering took us from 1,800 square foot calculators that required physical manual rewiring to pocket-sized devices packing hundreds of millions of transistors. We have truly mastered the art of shrinking the hardware and scaling the power. But with AI now natively integrating into our daily lives, I want to leave you with this provocative question to think about. What will the hardware of the sixth generation actually look like?